So if you recall, last time I was giving you a review of, at the end of the lecture, I was giving you a review of density matrices. And so I want to kind of continue that review by talking about CP maps and POVMs. And then after that, we'll get on to some stuff which is more likely to be new to you. So we have a system, and the density matrix can describe it even if it's a probabilistic mixture of pure states or if it's part of an entangled system. And so the goal here is to get into a situation where we can have part of a big entangled system, but we're only interested in part of it, and we can talk about the dynamics and the behavior of that part just by itself. And so the next step to do that is to try to think about operations that act on the system, even though they're not unitaries, because they involve interaction with some additional system, some ancilla state. And if you think about it, a density matrix, remember, is an arbitrary positive trace 1 matrix. Okay, so the most general dynamics that should be allowed on such a thing are things that always map density matrices to density matrices. And so what are those things? So So it's a CP-TP map, completely positive trace-preserving map. So it has the following properties. So first of all, it's a linear map. And this is essential, right, to the description of the density matrix as a matrix. That's implying that it has a linear structure to it. And so we want to preserve that linear structure. And so the operation that we're performing should also be linear. I guess maybe it's worth saying at a more fundamental level, linearity at the density matrix level is not quite the same as linearity at the Hilbert space level, right? Because if you take the sum of two density matrices, well, that's not a well-defined operation because the trace is then not 1. But you can take the average of two density matrices, for instance, or P0 times rho 0 plus P1 times rho 1. And when P0 plus P1 equal 1, then that's well-defined density matrix. But what it represents is not a superposition of rho 0 and rho 1. It represents a probabilistic mixture, where with probability P0 you take rho 0 and probability P1 you take rho 1. And so saying that the operation is linear is not saying that it's linear in the Hilbert space sense. It's saying that it's linear in the probability sense, which is kind of even more fundamental. That you kind of expect that if you had probability of rho 0, probability P0 of rho 0, and then you do some map S to that, then you have probability P0 S of rho 0 afterwards. And that's just what that linearity is doing here. But we also then need to make sure that the thing that we get is not just a matrix, but it's a density matrix. And so since it started with trace 1, it should still have trace 1. And so we want it to be trace preserving. And that's what the TP part of this is. And it's a positive matrix. So we want it to be a positive map. And a positive map is one that maps positive matrices to positive matrices. OK? So that all makes sense. But it turns out that this is not enough. And this is where the C comes in. I guess this P is the positive. But we want is maps that are not just positive, but completely positive. And the reason is we want our maps, remember, the density matrix could just be part of a bigger system. And if we're only applying this operation to part of the system, we still want it to be true that the overall state remains a density matrix. So in particular, a completely positive map is one for which sorry, that's not right. For which S tensor I of rho AR is positive if rho AR is positive. OK? So this is saying that even if we act on part of an entangled state, we still get a positive map. And this is important because there are some maps which are positive which are not completely positive. The transpose is an example of that. So if you take, say, an EPR pair 0, 0 plus 1, 1, and you write down its density matrix and you do the transpose on, say, the A side of that, you'll get something that's not a positive matrix. You can work that out if you like. But this is the last condition. And if we have a map that's completely positive, that gives us, and trace-preserving linear, it gives us a CP-TP map. And any map that satisfies these conditions is an allowed quantum operation. So these things go by various names. They could be CP-TP maps. They could be quantum operations. Or quantum channels. OK? Questions on that? Yeah.
So what's an example of a map that is positive but not completely positive?
Right, that's the transpose is the example. Well, that's the standard example. And in fact, for qubits, that's sort of up to some ambiguity. That's the only example. But for higher dimensions, there are other maps as well. But transpose is kind of the nicest one in vector senses. Any other questions? OK, so it turns out that any completely positive trace-preserving map can be written in the following form, the Krauss form. Which is that S of rho is equal to sum over k, ak rho, ak dagger. And the AKs are arbitrary, except that they satisfy this condition, that sum of AK dagger AK is equal to the identity. And let's see. So the completely positive part is that sum of, so you get, if you do this and you have sum of AK dagger AK is less than or equal to the identity, that means the map is completely positive. And when it's equal to the identity, that also makes it trace preserving. OK? And that kind of makes sense, right? Because you can think of this as saying, well, there's a list of things that could happen to the state. That's the list of the AKs. And they happen with different probabilities, although the probabilities can depend on the state. And then we want those probabilities to sum to 1. And that's what makes it trace preserving. But if they sum to less than 1, it could still be completely positive. It's just that then we'd be losing some probability because there'd be kind of some missing operations. OK? So these AKs are called the Krauss operators. Now, the Krauss operators are not unique. Sometimes the ambiguity is pretty simple. Sometimes there's a lot of ambiguity. But you can always choose different sets of AKs. I mean, except if it's actually just a unitary operation, there's only one. But if it's non-unitary, then you can choose different sets of AKs that give the same map. But those are all perfectly valid. Another way of representing these CP-TP maps is via purification. So what you can do is you can say, well, And so this is another way you could imagine getting kind of the most general quantum operation. You can say, well, I'm going to take my state rho, and I'm going to add some ancilla, which might as well start in the state 0, because it's a new ancilla. It's not, could be anything, but so you might as well call it 0. And then we're going to perform some arbitrary unitary, entangling the two of them. And then we're going to take an ancilla, which doesn't actually have to be the same size or qubits as the original ancilla, and we're going to get rid of it. We're going to trace over it, throw it out. And what's left is S of rho. OK? And so this is equivalent. So first of all, any map that you get this way, rho to S of rho, is clearly going to be a completely positive trace-preserving map, right? Because fundamentally, it's a quantum mechanical thing. It's just a unitary on a bigger system. And so clearly, it has to satisfy all these properties, which were just kind of the basic properties we needed to be consistent with the quantum mechanical formalism. What's less obvious is that any CP-TP map can be written in this way. But that's true. It can be. So one thing that's worth noting that I kind of said when I was presenting this is that these CP-TP maps, we don't insist that they map a Hilbert space of a certain size, of a certain dimension, to a Hilbert space of the same dimension. It could be bigger. It could be smaller. You can even have CP-TP maps that that map, just a one-dimensional Hilbert space, which is just trivial, to a many-dimensional Hilbert space, right? And that's a CP-TP map that basically you can imagine as creating a state, right? It doesn't matter what. So in this picture, it's easy to understand how that works, right? You don't have any input really up here, but up here you have the 0 states, and you turn that into whatever big state you want. You trace over part of it to get a density matrix. It could be a mixed state, and that's the output. It's always the same state because there's only one input, the trivial one. And conversely, you can have a CP-TP map where you throw everything away. You don't have any output, which is also kind of trivial because you're taking all the input and you're ignoring it. But it's still a valid map under these rules. OK? Is there anything else I want to say? Nope. OK. So that's it for CP-TP maps. Are there questions on them? Yeah.
I guess it's not, but can observations, measurements be modeled by CP-TP maps? Or?
They can, sort of. The more standard way of modeling measurements is with POVMs. But I mean, you can. Yeah. So I mean, it depends on exactly what you want, right? Out of the thing. The thing is that this CP-TP map, you have a quantum input and a quantum output. Whereas a measurement, you have a quantum input and a classical output. So if you're willing to consider the classical output as really just quantum bits as output, then sure, you can just put them here, and it's just some regular linear transformation. The main thing that you would do, so here's what the purification of a measurement looks like. So normally, you'd go in and you'd measure, and you get quantum to classical. But suppose instead I take an ancilla, and I do a C0. And then I ignore this. OK? Well, the thing is that you could have measured this qubit just as well. And that's not going to have any effect on the state of this qubit. So that's kind of a moot point. But once you measure it, then you know that you've collapsed it. This one, right? If this is alpha 0 plus beta 1, then the state here is alpha 0, 0 plus beta 1, 1. So by measuring this one, we've collapsed the first one as well. So it's really just a mixture of 0 and 1 now. And so that's the sense in which it's kind of like this measurement up here, which is that you get a mixture of the classical 0 and 1. Now, the difference here is that in this case, it's still a quantum variable, and so it would make sense to say do a Hadamard transform to it. In this case, that doesn't even make sense. But that means that if you take this measurement and you get some classical bits, you weren't expecting to do Hadamard transforms. You guys can use some classical processing on that. And all of that can be done with quantum gates that are quantum versions of the classical reversible gates. So in that sense, yes, you can think of it as a CP2P map.
The gates.
I'm saying that so the measurement you can think of in this framework as well. And sometimes this is a very helpful thing to do, actually. But for the purposes of what I'm talking about right now, I kind of want to introduce another way of talking about measurements, which is the POVMs, which is more explicitly mapping quantum to classical. But before I do that, are there other questions on CP2P maps?
Do you require the composite system to have any specific properties?
So which composite system? So for this picture, the purification of the CP2P map, it's always going to be a tensor product with the ancilla. Over here, you mean for completely positive? No, this is an arbitrary density matrix. And in particular, if it's a tensor product state, then completely positive just boils down to positive. But if it's an entangled state, then you get some extra power out of this or extra restriction out of this condition. OK? Yeah, anything else? Any questions? OK. So then let's move on to POVMs. So POVM stands for positive operator valued measure. And so POVM is some set of operators MA, which are sometimes called the effects of the POVM. And the MA give us, so A runs over some index of possible outcomes of the measurement. And MA is then going to give us the probability of that outcome. So the probability of outcome A for the state rho is trace MA rho. And the MAs are not arbitrary. They should satisfy the following condition. Sum over A, MA is equal to the identity. Oh, sorry. And they're also positive. That's why their P is in there. And so this condition ensures that this probability is always a non-negative number. And this condition ensures that the probabilities sum up to 1. OK? So those are just kind of the two basic properties, again, that you'd expect out of a measurement that in order for it to be a sensible thing. I guess the third thing that's implicit here is that these are matrices. So this is a linear operation. Right? And so again, these are just kind of the fundamental properties you'd have to write down in order to make any sense of this as a representation of measurement. OK? So once again, well, OK, before I do that, so POVMs, they include both the kind of the standard projective measurements that you're familiar with, because then you can, so projective measurement you just say that each MA is a projector. I guess an orthogonal projector. Right? So you divide up the Hilbert space into sectors, and you have a projector on each of those sectors as direct sum of the sectors, I should say. And that's just kind of your standard von Neumann measurement. If the if the projectors have rank 1, they project on single states. That's kind of the most standard von Neumann measurement, but you can also lump different outcomes together to have higher rank projectors. But it also includes more general things. So for instance, you could say, well, with probably 1/2, I want to measure in the x basis. So I'm projecting on 0 plus 1 versus 0 minus 1. But with probability 1/2, I want to measure in the z basis, projecting on 0 versus 1. And that's a POVM as well, because then we have, in that particular case, we'll have 4 effects. We'll have 1/2 the projector on 0, 0, 1/2 the projector on 1, 1, and 1/2 the projector on the plus state, and 1/2 the projector on the minus state. Right? And we'll have 4 possible outcomes, which will tell us which basis we ended up measuring in and which outcome we got.
But does it sum up to 1 then?
Yeah, it does. So let me try that. So 0, 0 plus 1, 1, that sums up to 1. So this whole thing here is a half identity. And plus and minus projectors, they sum up to 1 as well. So this is a half. So the way I got them to sum up to 1 is by normalizing, by putting the probability of that basis in the 1/2 in the front there. OK, so but it also includes measurements which are not easily representable as projective measurements. You can have much more elaborate and complicated things. In fact, the number of outcomes, well, the number of outcomes can be arbitrarily large, but you can have other kinds of projectors. And the thing is that really you can take pretty much any positive matrix here. Well, yes, any positive matrix there, and any set of positive matrices. And of course, if they sum up to something that's not less than 1, then that's not going to work. But if you scale them down by a constant, right, then eventually, for some small enough constant, it'll always be less than 1. And then you can throw in what's left in order to make this add up to 1, and that'll be a POVM. OK? So so really, there's a wide variety of things you can do with POVMs. But once again, there's a purification theorem, which says that the POVM can be represented by extending the Hilbert space and then making some projective measurement. So you can think of it, for instance, like this, where we again do unitary, and then we do some projective measurement here. Now, this particular representation of it would be a complete measurement, where you have kind of full information about the outcome. But the POVM doesn't do that. It might, again, lump together various outcomes. So there might be some classical post-processing. So for instance, if you have a 3-dimensional Hilbert space that you're measuring on, and you measure in the standard basis, you get the outcome 0, 1, 2. And that's an allowed POVM. But you could also say, well, I want a 2-outcome POVM, with 0, 1 being the first outcome and 2 being the second outcome. That's also a valid POVM. OK? And when you're doing this more complicated thing, you may well have to do that in order to represent your actual POVM in terms of this purified version. Yeah.
You say that each EMA is an orthogonal projector?
Well, yeah. So this is the standard, kind of the standard projective measurement. Has them. Yeah. So this is not a standard projective measurement, right? This is a mixture of 2 different projective measurements.
Oh.
So this is a very special case of a POVM, but it's the special case is kind of taught in undergraduate quantum mechanics. So I wanted to make contact with that. Any other questions? OK, so yeah, so the bottom line is that you can have a big entangled system and then just focus on understanding the dynamics of density matrices in a small subsystem, provided you don't need to interact with the other parts of this big system. You can do operations by doing CP-TP maps on that density matrix and update the density matrix accordingly. And the measurement, you see, is just a function of the density matrix, provided you're only measuring this one subsystem. Now, of course, if you want to interact this subsystem with a different subsystem that's something that it's already entangled with, then something more interesting can happen that's outside of this framework. But then you shouldn't be talking about the density matrix of just one subsystem. You should be talking about the density matrix of all the subsystems that you're interested in. And then all of these operations have these purification pictures. So if you're not really comfortable thinking about density matrices, the bottom line is you don't have to. You can always think of what's going on as a pure state where we're just kind of ignoring part of the system, right? And unitaries where there's some additional states floating around somewhere, ancilla qubits or whatever, that we bring in when we need them and then we throw away when we don't need them. Yeah?
So in the purification of the POVM, you're not purifying the density matrix, you're purifying...
You're purifying the operation, the effects, yeah, sort of. I mean, yeah, in some sense, yeah. I mean, you can also purify the density matrix, right? There can be some reference system up here. And I mean, yeah, so it's important to note that that still works. That, I mean, POVMs don't really have an update rule usually associated with them. But usually they're done in the case where you're done with whatever operations you want to do, and now you just want classical outputs. But if you were to do it this way, of course, you could say, well, conditioned on this outcome, what's left over up here? And that has to make sense too. OK, so let's, in that case, move on to some other properties of states. And in particular, one thing that shows up a lot is you want to say, how close are two states? So I want to say how you can define that, right? That's actually a kind of subtle question. So we have two different quantum states. And so first of all, why does this show up? Well, for instance, if I have time today, and certainly tomorrow and Friday, I'll be talking about how you build a quantum computer. But of course, real experiments are not perfect, and they want to be able to say, well, we got it almost right. How close are we? So you need a way of saying, how close are you? And when you're talking about error correction, of course, it's also very important, because you don't expect to be able to correct arbitrary errors. You want to correct errors in states that are kind of close to the right one. And you don't necessarily expect to get it perfectly. You want to get it closer than it was. So you want to say, how close is it? But it shows up in a lot of other places as well. In algorithms, for instance, you might not be able to get exactly the state that you want with a relatively small number of gates. But if you can get close enough, then maybe that's good enough to give you the answer, the correct answer at the end. So things like this show up all the time. OK, so one kind of natural, if you're talking about pure states, one kind of natural measure of distance is the fidelity. And so when we have two states, psi and phi, looking at the inner product with them, that's a good way of saying how close they are, right? Because if psi is equal to phi, then that inner product is 1. And if psi is orthogonal to phi, which seems like the farthest apart you could be in Hilbert space, then the inner product is 0. Of course, this thing here is a complex number. So that's not actually a good thing to look at. What we really want to look at is this, the absolute value. And that's a real number between 0 and 1. And then 0 means it's 0 if and only if they're orthogonal. And it's 1 if and only if they're the same. And otherwise, it's somewhere in between. And there's a concrete operational meaning to this fidelity here. So in particular, if you say, well, I think I have the state psi, but it might be phi. I'm not really sure. So let me project on the state psi. Or the orthogonal subspace to psi. And then what's the chance of getting the outcome psi? Right? If the state really is psi, then 100% of the time I'll be right. I mean, I'll get that outcome psi. But if the state is phi, then I might sometimes get psi and sometimes get 1 minus psi. And what is the probability of getting psi? Well, the probability of that is f squared. Right? If you have the state phi and want to project on the state psi, that's the probability of getting that outcome. Okay, so this is an operational interpretation of this fidelity measure. Okay, but the thing is that this is just for pure states. And I just went through a whole business where I was explaining how we can talk about density matrices and we don't have to worry about the rest of the system. So how do we do that in this case? What's the fidelity between density matrices? Well, if we have a pure state and a density matrix, which is actually a pretty common situation. So for instance, experimentalists might say, oh, I want to get this pure state, but actually I have a density matrix. Then there's a fairly obvious definition, which is, so this is the fidelity between psi and sigma, and it's allows you to talk about the square of it. That's just the trace of psi sigma. And you see, when sigma is a pure state, this boils down to the same thing there, right? Because you plug in phi phi here, you get psi phi, and then by the cyclicity of the trace, phi psi. So it's the absolute value squared, which is exactly what you should get. So that's good. So this is certainly generalizing that. And it has the same property that it's 0 if they're orthogonal, which means that psi lives on a subspace that's orthogonal to the support of sigma. And it's 1 only if they're the same, if sigma is actually the pure state psi. But the problem is this is not the most general case. We want the fidelity between two density matrices. And that's a more complicated formula, which basically you could never guess by yourself. Here it is. So it's the trace of the square root of the square root of rho sigma square root of rho. Now, these square roots are well defined because these are all positive matrices, remember? So for instance, if you diagonalize them and then take the square root of the diagonal elements, and then you undiagonalize, you go back to your original basis, that will find the square root. So it's kind of like, it's kind of like the square root of trace rho sigma. And in the, well, OK, yeah, not very much like that because this square root is inside the trace rather than outside. But the thing is, this you get 1 power of rho here. You have rho to the 1/2 and rho to the 1/2. But because rho and sigma might not commute, this is not the same as rho sigma. And then we have to take this square root, again, basically for this reason. Anyway, so this thing specializes in the case where, say, rho is a pure state to this. So it is a generalization of the standard fidelity, but it has a bunch of other properties which are not so obvious from the definition, maybe, but happen to be true. Let me put them over here. So first of all, it's always between 0 and 1. And it's equal to 1 if and only if rho equals sigma. So let's see. So if rho does equal sigma, that's fairly obvious, because in that case, square root of rho and sigma do commute. And so this is going to be rho squared. And then the square root gives you back to rho, and trace rho is equal to 1. It's probably less obvious that this direction holds, that the fidelity is equal to 1 only if the density matrices are the same. But it's true. And again, fidelity is equal to 0 if and only if rho and sigma have orthogonal support. So support of a matrix, in case you don't know, is the subspace on which the matrix acts non-trivially. So for instance, you could write the matrix as something which is the direct sum of some non-trivial matrix on the support plus zeros elsewhere. And here's one which is pretty basic, but is really not obvious from this definition, which is that it's symmetric. That the fidelity of rho sigma is equal to the fidelity of sigma with rho, right? Because this definition is not obviously symmetric at all, right? It's treating rho and sigma differently. OK, so here's another important one. And this one is maybe not too hard to see. So if you take two density matrices, rho and sigma, and you rotate them both by some unitary u, then the fidelity should be the same between them. That's a good property that we want. And that's true. Now, on the other hand, if you do some arbitrary CP map on both of these things, it's possible that the fidelity won't be the same. Why is that? Well, as an extreme case, remember that map, that CP map, which took the input and then just threw it away and put some standard output state. Well, obviously, no matter what two density matrices we have to start with, the fidelity of the outputs will be 1. But it should not be the case that any CP map can make two states more. So it's certainly the case that CP maps can make two states less distinguishable, right, by throwing away some information. But it should not be the case that it can make them more distinguishable, right? And fidelity is a measure of distinguishability. So it must be the case, and you can calculate that it is true, that the fidelity of these two things, of S of rho and S of sigma, is greater than or equal to the fidelity of rho and sigma. That's saying that the images are closer together. They cannot be further apart. OK? And then there's one more property, which is the one that really nails down that this is the correct definition. And that's Ullmann's theorem. So the fidelity of rho and sigma is equal to the maximum over all states psi and phi with some property of f of phi and psi. So this is the pure state fidelity. And so phi and psi are purifications of rho and sigma. So that means that trace over R of phi is equal to rho, and trace over R of psi is equal to sigma. So we can say phi and psi are acting on our original Hilbert space plus some reference system. Okay? So this is saying that if you take rho and sigma, and then you want to think in this curve larger Hilbert space version where you purify everything, we can do that. But remember, the purifications are not unique. And so if you adjust the purification so that they're as close together as possible, that gives you the fidelity between rho and sigma. Okay? Now, if you imagine kind of some general purifications, phi and sigma, and look at the fidelity between them, it might be less, right? Because you haven't adjusted to be the best. And it's very easy to do that, right? For instance, you can tensor product for rho, you can tensor product with the state 0. And for sigma, you can tensor product with the state 1, right? And now they're orthogonal, the purifications. And so the fidelity would be 0. But of course, when you drop this reference system R, that's a CP map. And so we know that the fidelity can get larger in that case. It can't get smaller, but it can get larger. Okay? But when you pick kind of these optimal purifications, then it doesn't. Okay? So sometimes people also talk about the infidelity, which is just 1 minus the fidelity. And the reason for that is because if you want to think about this more like a distance, then it's a little awkward to have the same state. If phi and psi are the same, fidelity is 1, but the infidelity is 0. Okay? And so it's a little awkward to say that two states are the same when the distance between them is 1. Right, you want the distance to be 0 then. OK? So are there questions on the fidelity? Yep.
I guess it's a question about distance measured, not exactly fidelity.
Mm-hmm.
I mean, I guess, if I have state phi and two states psi 1 and psi 2, and they're, say, both orthogonal to phi,
Mm-hmm.
then there's no way of distinguishing which state is further away from phi.
Right. And so in the kind of the abstract Hilbert space picture, is that they're the same distance from. I mean, it doesn't really matter, right? I mean, so think of a very special case of that. Phi is a state 0. We have a 3-dimensional Hilbert space. Psi is 1, or psi 1 is 1, and psi 2 is 2. Right? Which one should be closer to 0? They're just 3 orthogonal directions, right?
Right. I guess I was thinking like maybe physically it might be easier for a given Hamiltonian to get to psi 1 but not psi 2.
Sure.
And then
sure.
you would have to have a notion.
Yeah. So this is certainly not the be-all and end-all of notions of distance. And in fact, I'm just about to tell you a different notion of distance, although it still doesn't address that particular question. But you can certainly come up with other notions of distance. Yeah. I'll just leave it at that. But I should say that what you're talking about is actually, in some sense, completely unrelated to fidelity, because it can be that you have two states that are very close, but your particular Hamiltonian doesn't let you move between them, or it makes it very hard to move between them. Right? Very close in the fidelity sense. So it's a totally different notion. Any other questions about fidelity? OK, so the other somehow I ended up on this side of the board, but the other notion of distance that people talk about a lot is called the trace distance. And so this one is kind of easiest to define right away for density matrices. We don't have to go through this whole derivation with pure states. So the trace distance between rho and sigma is a half of the trace of the absolute value of rho minus sigma. Okay? So in the case when rho and sigma are diagonal, just classical probability distributions, this reduces to something called the classical statistical distance. So if we have a probability distribution pi and a probability distribution qi, then it's just the sum of the absolute value of pi minus qi. Okay? So this is saying, if you look at each outcome, what's the kind of the difference in probability of getting that outcome between the two distributions, without saying which one is bigger and which one is smaller. And then we're just going to add all those up. Okay? And so then the trace distance is the quantum generalization of that, pretty natural quantum generalization. And in fact, if rho and sigma are simultaneously diagonalizable, then you can do that, and this is exactly what you get. But more generally, you could diagonalize rho minus sigma, right? And then you get some eigenvalues of rho minus sigma. And some of them, now this is not, rho is a density matrix, sigma is a density matrix, they're both positive. But the difference between them is not positive, clearly, and has trace 0 rather than trace 1. And so when you diagonalize, you're going to get some positive eigenvalues and some negative eigenvalues. If we would add up the positive eigenvalue, it has trace 0. So if we just took the trace, we would get 0. But if you add up all the positive eigenvalues and take the absolute value and add up the negative eigenvalues as well, now you're getting something different, right? And that's where the trace distance comes in. Okay? So yeah, so like fidelity, trace distance has an operational meaning. So the trace distance is the maximum over POVMs of the classical statistical distance let's see, POVMs E sub m between trace rho EM and trace sigma EM. So in other words, if you want to kind of maximize the distance between, if you want to kind of best distinguish between rho and sigma, you figure out the best POVM to do that. And the best one will be the one that has the biggest statistical distance between the outcome probability of measuring that POVM on rho versus the outcome probability of measuring it on sigma. And the reason that this is the best thing to do is because this lets you give the best guess of whether you have rho or sigma, presuming you had 50% chance of each. So somebody gives you rho with probability at 1/2 and gives you sigma with probability 1/2. Your goal is to guess which one it is. And that probability will be given by doing this best POVM. And then your probability of getting it correct is 1/2 1 plus d of rho sigma. You can always do at least a half, right? Because you just don't do any measurement and just guess. But if the states are very distinguishable, if they have a large trace distance, then you should be able to usually or always get it right. Whereas if they're very, very, very similar, then you should not be able to do much better than a 50-50 guess. And so the proof here, well, how do you make that best guess? So what's the optimal POVM? So you take the subspace, so it's a projective measurement of positive eigenvalues of rho minus sigma versus the negative eigenvalues. Okay, so you look at this, you do this unitary so that the rho minus sigma is diagonal. And you say, well, in one subspace, we have positive eigenvalues, which kind of means it's kind of more like rho. In another subspace, we have negative eigenvalues, which means kind of more like sigma. And this is the best measurement you can do to distinguish between them. If you're in the positive eigenspace, you say it's rho. If you're in the negative eigenspace, you say it's sigma. And if you calculate it, that gives you, well, first of all, it gives you this probability of the outcomes. And you can't do better than that. And your probability of guessing rho right is this, or guessing whichever one you actually have is this. OK, obviously, I didn't go through all the details of the proof, but that's the main idea. OK? So then, again, this trace distance has a bunch of properties, some of which are more obvious than others. So again, it's between 0 and 1. And the trace distance between rho and sigma is 0 if and only if they're the same. So that should be pretty obvious, right? Because certainly if they're the same, then this is a 0 matrix, and its trace is 0. If they're not the same, then this is non-zero. And so it'll have some non-zero eigenvalues. And when you're adding them up, the absolute value of them is always going to be positive. So you can't get back to 0. This one is also pretty straightforward. D of rho sigma is equal to D of sigma rho. It's, again, not symmetric, but in that case, it's easily taken care of by the absolute value. And this actually is a genuine distance measure. It satisfies the triangle inequality. So the other property, remember, that we had for fidelity that was important was that it was unitarily invariant. And that's still true of the trace distance. And similarly, if we have a CP map, the CP map can make states less distinguishable, which means making the trace distance smaller, but they can make them more distinguishable. So d of s of rho s of sigma is always going to be less than or equal to d of rho sigma. So this is for unitary U. This is for CPTP S. OK? OK, And then I guess the last thing I wanted to say about trace distance is that it's not totally independent of fidelity. It's a different measure of distance. They don't go in a one-to-one correspondence. But when two states are very close together in trace distance, they're also very close together in fidelity. Fidelity is close to 1, trace distance is close to 0, and vice versa. And that's captured by the following theorem. 1 minus the fidelity is less than or equal to the trace distance, which is less than or equal to square root of 1 minus the fidelity squared. Okay? So this kind of gives you bounds on how different they can be. But for some pairs of states, you'll be on one side of this bound, and for some pairs of states, you'll be on the other. So it's not, you can't really tighten this much in the general case. OK, so there are questions on these things. Yeah.
I'm a bit confused about the CPTP map that for the trace distance, it is decreasing.
Yeah.
For the fidelity, it's increasing.
That's right. And that's because for the fidelity, when they're the same, the fidelity is 1. And for trace distance, when they're the same, the distance is 0. So you're kind of going towards the close case in both cases. Yeah, so it's more sensible to compare the trace distance with 1 minus the fidelity. Yeah.
Can you explain again why CTPT maps will make states go get closer together?
Yeah. So basically because they can throw away information. So if you think of it in this picture, remember that the thing that's getting thrown away here doesn't have to be exactly the ancilla, right? So we can kind of, but even if it is, this unitary can be kind of taking some of the information about rho, and it ends up in the crash count, right? So that information might be information that's used to distinguish rho and sigma, right? And so if we're throwing it away, they might become less distinguishable. In the extreme case, we could throw everything about rho and sigma away, remember, and then we're left with just some constant state, and it's always the same. We can't tell them apart at all anymore. I mean, this is kind of a special case of a more general property that you see, which is that anything you do in a system can lose information, but it can't kind of generate new information that wasn't already there. OK, I think probably I should not start a new topic in the last minute. So are there any more questions about this? OK, so then tomorrow we're going to start to talk about implementations, how you actually build a quantum computer. And that will be at the regular time. So hopefully no more of these switches. You'll be able to sleep later. And so, well, I won't really be able to sleep later because I have a son, a young son. But anyway, see you tomorrow.